Hi, welcome to another session where we will be solving this unsymmetrical bending problem. And I have already drawn the section that we are going to be working with. And also I've written down what is asked in this exercise. For example, we have the first thing to notice or to see here is that we need to find what's the position and direction of the principal inertia axis. Then after, when we say position, it means two things. Position and direction, it means two things. The first one is where would be the origin or of that system representing the principal inertia axis. And the second one, the direction, means so how it's going to be oriented with respect to something we have here, for example, the vertical and horizontal axis. After that, we're going to move and start calculating what is the magnitude now of the principal moments of inertia of those second moments of area around those principal inertia axes. And remember that we need that for stress calculation purposes. Then the third thing would be that we need to find the position and direction of the neutral axis. And this is pretty important for the fourth step, where knowing now how that neutral axis is oriented, then we can determine what's the farthest away point in the section that is going to, let's say, allow us to calculate what's the maximum stress as it is asked in the fourth step. Calculate the maximum stress, considering that we have a beam in cantilever, meaning that we have one end fixed and the other one end is free. Then the shape of the section of that beam is this L shape, like it is presented here. And then we're also going to consider that there is a load of 2000 newtons applied at the end or at the free end of that cantilever. And important thing to say or to mention here is that the line of action of that force passes through the centroid of the cross section that we need to determine, or we should have determined already during the course of solution of the problem. Now, in the image that you see here, the representation of the L-shaped section, I've tried to make it or draw it a little bit coherent with the dimensions. For example, I've tried to use a certain, or try to respect the scale of the dimensions so we can see more or less clearly where in reality, for example, the centroid of the cross-section is located, or how the axes are inclined or oriented, so we can have a close to real representation of this problem. Perfect. After describing all of this, at the end, so we need to find a few things here. I'm not going to bring at once the equations we need to use, but I will be bringing them as we need them. So we can follow a nice flow that can be used for you to solve any other type of unsymmetrical bending problems. So in this case, we need to notice a key thing is that, as mentioned in the lectures, most of these figures or elements, members we're going to be working with, they are most probably formed by rectangular sections. For example, you see here that you have a horizontal rectangular section to represent the upper part of the L, inverted L, and then you have another rectangular section here to represent the vertical part of it. The first thing we need to do then is to locate the centroid of the cross section, and the centroid definitely differs from the centroid of each one of these figures. So we are going to consider that we have to facilitate things, that we have two rectangles. So we have this rectangle here. On the top, I'm going just to try to mark it like here, like this. So we have a first rectangle. We can mark it like 1 here. And a second rectangle marked like as 2 here. And then we can say that, well, to find out what's the value of the or the position of the centroidal axis, well, we need to measure things with respect to something. And what I'm going to do here is I'm going to say is that, well, you know what, my origin is going to be something like in here, in this corner on the top. And I'm going to consider that this is going to be, I'm going to represent all my calculations with respect for the centroid location. I'm going to represent it with this type of reference system, where x is going to be measured positive going to the right, and y is going to measure positive going downwards, in this case. Now, if we remember, the formula to calculate the position of the centroid of the combined cross-section is something in general like this. Where should I write it? Maybe here. Yeah, here. It's 1. So we're going to have that the centroid, for example, x position is going to be defined by this general formula is going to be equals 1, 2, n. So where n represents the number of sections that I'm dealing with. In this case, I'm dealing with 2 sections, different because I split the combined L shape into 2 parts. And then this is going to be equal to multiplication of the area of the section times the distance x. And this distance x represents the distance from the origin that I'm taking right now, which is here. Let's mark it as a O. The origin, and the position of the centroid of each section. So what does it mean? It means that for the upper rectangle, I'm going to have a centroid for this figure, if I forget about the second section here. So, and that centroid is going to be located, as we know, for the rectangle in the center of it. So it's going to be located something like here. Yeah, and then it's going to be kind of half of this measure here is going to be 30 millimeters, and then downwards is going to be 5 millimeters. Now for the second section, it's going to be, well, half of this. So this is 90 millimeters. So it's going to be right about here. So it's going to be at 45 millimeters measured from the bottom here, and then it's going to be 5 measured from the left here. So I'm going to call this x1, y1, and then I'm going to call this x2, y2. Well, this formula is not over because this needs to be divided by the sum of the areas. Again, this is from 1 to the total number of elements or sections I'm considering. And for y, well, you must suspect that it's kind of the same. So, but considering the y coordinate divided by the sum of the areas here, equal 1 to n. Okay, let's first find the values of those x1, y1, or, well, we already know of that, but let's kind of write them down so we have them at hand. So, okay, first, maybe here we can keep it with the figure in case we need to copy the figure. We always, no, let's write here. So x1 is going to be equal to, we mentioned that it's the distance from the origin to this part. So that's going to be 60 divided by 2, which is 30 millimeters. Let me write it completely so you have it as a reference here. Stroke eraser, so 60 divided by 2 equals to 30 millimeters. I'm going to write down the units at the end. Then y1 is the vertical distance from 0 to the centroid of the first section, and that's going to be 10 divided by 2, and that's going to be 5 millimeters. x2 is going to be the distance from this vertical left line to the centroid of this section, and that's going to be also 10 divided by 2 equals to 5 millimeters. Then, component in y direction of the centroid of section 2 of area 2, it's going to be then how would I reach from this origin to the center of this figure here, of this section? And then it means that I have to transit this 10 millimeters and then half of the 90 millimeters here. So it's going to be, if I wanted to write it completely, it's going to be something like this: 10 plus the 90 divided by 2. And that's going to be 45 plus 10 is going to be 55 millimeters. Now, another thing we need to find out is the area of each one of these sections. And then where should I write? Let me write it here. So A1 is going to be equal to what? Well, if I consider this, the first area is going to be it's going to have a base of 60 and a height of 10. So it's going to be 60 times 10 equals 600 millimeters. And then area 2 is going to be what? Well, this vertical, or, well, not vertical, but second area or section is going to have a base of 10 millimeters and a height of 90. So it's going to be 10 times 90 millimeters, and that's going to give us 900 millimeters. And with this, we have all the ingredients needed to. Let me put this a little bit closer. And this one also. So we have more space to operate. This one here also, and this one here. Perfect. What is left is just we need to substitute these values into these formulas that I have written down here at the beginning, and then we will find how much are those values. So let's do it. To go down a little bit so to keep track of that, and then finally, let's put it here. Yeah, the position of the centroid of the combined cross section is going to be equal to what then? Well, it's going to be equal to area 1 times x1. Let me just write them down nicely. Plus area 2 x2 divided by area 1 plus area 2. And that's going to be equal to what? Well, we're going to have 60, sorry, there is a mistake here. This is square millimeters, the area. Yeah. So 60, let me write down the units because I don't want to make this mistake again. So this times x1 is 30 millimeters, plus area 2, which is 100 square millimeters, times x2, it's 5 millimeters. Then this is going to be divided by, perfect, this is going to be 600 square millimeters times plus 900 square millimeters. So let's jump to GeoGebra to make these calculations. So let's go to this one and this one here. Let me come back a little bit to just try to make it a little bit smaller so I can see what are the values that I need to be seen here. Yeah. So I'm going to have that, can I write x1 maybe? Yeah, equals to 600 times 30 plus 900 times 5, and that's going to be divided by 600 plus 900. And that's going to give us 15. Perfect. Should I make this a little bit bigger so you get to see it? Yeah. Just let me put it like this in here. Yeah, so x1 is 15 millimeters. So let's go back to OneNote. This is going to be, oh, sorry, it's not x1, it's just x, 15 millimeters, because this gets canceled out and then there's no, so no, it's not x1, it's 15, it's just 15 millimeters x. And let me go back to GeoGebra to try to have a nice, there you go, yeah. X. Let me call it centroid. There it is. Perfect. Now, what that just means that, you know, that the, how to call it, that the position of the centroid is 50 millimeters to the right of this origin here. And if I wanted to, as I have drawn this in some sort of kind of more or less at scale, so it would mean that that axis, let me use this color here, is going to be somewhere, let me try to have a shape here, more or less, it's going to be like in here, more or less there. There, that's more or less 15 millimeters from this distance here. And let me just clean it a little bit so to make it look like it is a line that represents some axis of symmetry. So this one here, this one here, and so on. There it is. So this distance here, I'll mark it with these double arrows here, is going to be this x bar here that we have just found. Perfect. Now let's find the y distance or the y position of this centroid of the cross section. So to that end, I could mark this down. So this one, let's go with y. The position that is going to be, then again, just translate the equations there. 1 plus a2 y2, and that's going to be divided by the sum of the areas, a2, and equals to what? Then let's continue. So we have all the data for this. So we have 600 square millimeters times 5 millimeters, which is the vertical direction or distance from the origin to the centroid of the first section, plus then 900 millimeters, square millimeters, sorry, times the y distance is 55 millimeters. And that's going to be divided by the sum of the areas, and that is 600 square millimeters plus 900 square millimeters. How much is that one? So let's calculate it. Just let me write down here y. Let me write it better like this. Let's go to GeoGebra to calculate that. Now we have it here, so it's not on. So here it is. So now we are with y centroid. So 600 times 5 plus 900 times 55, and that's going to be divided by the sum of the areas, like this one, 35 millimeters. Let me write it down. Let's go back. Here it's 35 millimeters. And I can mark this again with this color, so to just highlight it or to single it out. And that means that the distance from this horizontal line to downwards vertically, so that's going to define us the position of the other inertia axis. Let me write it down where. So it's going to be 35, so we have 10, 20, 30, something like in here. There is going to be our, let's again fix it, like to make it kind of a symmetry axis, sort of like this. Let's put the dimension of the distance that we are representing here, which is this one here. There you go. This is then y bar. Then we have found the position of our centroid. So this is one of the things that were asked in the problem. This is a centroid, and sometimes it's represented as G. Awesome. So we found just the first one. So now we need to find what's the value of what is the direction or orientation of those axes, because now we have just found the position of the centroid, and that's it. But we know that those principal inertia axes are going to use that centroid G as the origin for the references that they are creating. Then we just need to find the angle between the horizontal or vertical of these lines that I have drawn here as symmetry axes to some sort of symmetry axis. They are not perfectly symmetry axis because this is an L shape, so it's not a symmetry axis, but they are axes, represent some kind of to represent it away from other type of references or lines there. So to do that, let's remember that in the formulas, we know that we can calculate the orientation from this horizontal line, this one here, to one of the principal inertia axis, just by using a formula that was derived during the lecture. And that formula would be nice if I could bring this with me, because we're going to need it. So let's repeat this equation, this in several parts here, in here, in here. Yeah. So that angle is going to be represented by the tangent to theta. That theta is the angle from the horizontal line that I have there marked there. It's going to be equal to 2 times the product of inertia divided by the moments of inertia. Actually, this is the subtraction of this moment of inertia. So what it means, this means that we need to calculate the moments of inertia with respect to this xy or an xy direction here, represented here, and then use that information to calculate this angle theta, which is the angle from the horizontal line here to the one of the principal inertia axes. So let's start calculating then the moments of inertia or second moments of area and the product of inertia of this combined cross-section. Now, as we're dealing with combined cross-sections, it means that we need to use some specific way to calculate the moments of inertia. So we know that for rectangular areas, I'm going to write it down here. For rectangular areas, rectangle. So we know that the moment of inertia equals to the base, like b, times the height, like h, power of 3, and that's going to be divided by 12. Yeah. And that is when we are dealing with when we are calculating the moment of inertia or the second moment of area of a rectangular section with respect to the centroid. Let me try to bring a figure for that moments of inertia rectangle. It's to be image, and there's one simple image here. This might be nice to have. Yeah. Let's see if I can copy it. Yes, here it is. Let me just put it here. So then this formula only applies. This uses the masses. Now I want the area. Sorry about that. Let me find a better inertia of the areas. Maybe this one here. Let me see if this one looks fine. It's still not looking good. Yeah, this might be the one. Now, the important thing with this formula is that the moment of inertia has to be measured against with respect to something, a position. And in this case, for this formula we are using here, it means that, it refers that we need to calculate that moment of inertia, or is telling us the moment of inertia with respect to the center of the rectangle here. So that's important, and it's important for the next thing we're going to do, because you're going to find tables that they say, well, what's the moment of inertia of a rectangular section that is, with respect to one of the corners, for example. You can find such formulas. But then when we are dealing with the second moments of area, you need to know exactly where is that being measured from. In this case, well, it's measured from the center of things. And it's good because we have already represented the center of each one of these sections here, which is going to allow us to, let's say, continue this calculation. Now, yeah, well, this is perfect, but if I want to calculate the moment of inertia of the cross-section, well, yeah, you are giving me the moment of inertia of the rectangular section, but as I mentioned, moment of inertia refers to a point and an axis about. But no, I need to calculate it not on the centroid of the section, but on the centroid G of the cross-section. So if that's the case, so how do I represent the moment of inertia that I know with the moment of inertia that I need to calculate? And also, how do I combine it with the other section here? Well, one of the things that we need to use here is the parallel axis theorem. That's the one that's going to allow us to calculate these quantities. Let me write it down. Parallel axis theorem. Then it's also called actually it's also called Steiner's theorem. Just let me, because it's been a while. Steiner's parallel axis theorem. So you're going to find also like this. It's been a while since I have mentioned this name. Steiner's parallel axis theorem. Yeah. And it says that, well, the axis is, well, that, how to call it, that moment of inertia that we need to calculate needs to be take into account that the distance or the position of the centroid of the section is different than the position of the centroidal point that we need to calculate around what did that. So that is that we have that the moment of inertia in x is going to be a sum of things, like it's going to be the moment of inertia of the first area plus the translation of that moment of inertia represented on the centroid of the section to the point G. And that's going to be represented by the area of the section times something here. And that something there is going to be the distance in y, if we're talking around the x-axis, so the distance in y of the position of the centroid of the section to the point G. And let me just write it down. How should I put it? Because it's not just, it's a distance. So let's put it like this. It's not completely correct, but just to differentiate from the other y1 that we have written. And then this is going to be plus something, and which is going to be the moment of inertia of the second area with respect to something known, the origin, that is the centroid of that second section. Then that's plus area 2 times what? Well, the distance or the difference in distance from this second point here and the moment of inertia, and how to call it, and this point here. So it's a bit confusing, but I'm going to just to leave it open. So actually, let me write it better here so not to make it so confusing. I'm going to call this, let's call it like this, and let me call this like this. Now we will represent that. So let's just, and then for the y, it's going to be the same. And again, this is xx, xx, and then for the y, we're going to have that y1 plus area 1, and then let's write this one like this, plus, then we're going to work with the second part here. Now having those two, I believe we need to define those y1 bar and y2 bar and the other ones. So let's do that. So let me just get rid of this figure because we don't need it anymore. Like this. And let's see, so how much are those values here? So the distance from this point x1 to, or this x1, y1 to vertically to this part here. Let's see. So that's going to be, actually, it's like, let me mark it in this one. So y1 is going to tell me this distance here. So it would be something like this. I call it like that. Yeah. So how much is that? Well, is the difference between the y position of the centroid of the cross section minus the y position of this one here. So it would be y1. Yeah. So let's write it down here. y1 is going to be equal to what? Well, it's going to be equal to y is 35, as we have written down here, 35 millimeters, minus the vertical position of this centroid of the first area. It's going to be 10 divided by 2, or it's just y1, and that is 5 millimeters, equal to 30 millimeters. Perfect. Now, how much is y2 then? Well, let's mark down y2 with the same color here. So it's basically this one here. Done. Now I kind of have to keep consistency. And there are several ways we could do it. So we can have, for example, a line here, the base, like this, and we could say that, well, that this distance can be, for example, how much is the distance from the G point to the base, and then I can subtract what is this distance, vertical distance on the top. So that would be something like I could say, well, you could let me use another color. Take this value here, and that value is going to be how much? So if I know that y is 35 and the whole height of the cross section is 100, then the remaining part here is going to be 75 millimeters. And I also know that the distance from this part here, from the centroid of the section 2 to the bottom here, this is going to be 45 millimeters. Then y2 is going to be equal to 65 millimeters minus 45 millimeters. And that's going to be 20 millimeters. Now we have all the ingredients to calculate these two values, the moment of inertia around the x-axis and then the moment of inertia around the y-axis. So let's do it now. So let's see, let's start with, let's use this color just to change. I think it's going to fit here, yeah. So, okay, so the first moment of inertia about the x-axis is going to be this one, this formula here, and that's going to give us base times height to the power of 3 divided by 12. So base is 60 millimeters times height, this 10 millimeters to the power of 3 divided by 12, plus the area, and the area of the first element is 600 square millimeters, times the distance y1, y bar 1, and that y bar 1 is 30 millimeters. Let's continue with the second row here. Then we have the moment of inertia of the second section with respect to its own centroid, and that's going to give us 10 millimeters times 90 millimeters. Again, this is 90 millimeters square, to the power of 3 divided by 12, plus the area of that section, which is this one, times the y bar 2, and y bar 2 is how much? Well, how much it is? We said that it was 20 millimeters. There is one missing piece here, and I apologize for that. This has to be square in the formula. Almost missed it. Now let's go to GeoGebra to calculate this, and let me just write down this one here. This one in here. All right, so let's start with the first fraction, and that I should let me see if I can do this. Fraction is going to be 60 times 10 to the power of 3 divided by 12, and then plus 600 times 30 to the power of 2, plus 10, here is plus 10 times 90 to the power of 3 divided by 12, plus 900 times 20 square. And that's giving us, I'm going to write it down before I kind of come back to one node here, and that's going to give us 1 5 1 2 5 0 0 1 5 1 2 5 0 0, and the units are millimeter to the power of 4. We mark it down like this. Nice. For y is the same. Now we need to find out how much are, what could be a nice color, this one. How much are this small piece here. This is going to be x2, x bar 2, and then how much is this one here. And well, this is easy because, well, not easy, but presents a similar case than before. So now we can write down, apply the formula here for xy. Let's write it down here. Moment of inertia of the cross-section about the y-axis. Now by changing the perspective or the orientation of what we're doing, or what's the axis we are calculating the moment of inertia, then the relation base and height of each one of the area changes. So it's going to be something like that. So when looked from with respect to the y-axis, so we need to know that the base now is going to be kind of the vertical part here, because now we're talking about distances with respect to the vertical axis that crosses or passes through the centroid of the section. So it's going to be something like this. In the first case, for the first area, now the base is going to be 10. The height is going to be 60, because now we are changing the perspective here. And just put it like this. Let me write down the units. 10 millimeters times 60 millimeters to the power of 3 divided by 12 plus the area, and the area is 600 square millimeters, times this x1. And now, well, we haven't calculated x1, but in this case, it's a direct measure x1. We can write down here. All kind of is readily seen that x1 equals to 30 millimeters. And x2, and again, this is not correct. This is x2. Then is how much is this? So basically, it's just dividing or subtracting x minus this distance here, which is 5, and that's going to be x is 15, if I remember correctly, minus 5, and that's going to give us 10 millimeters. Okay, we're here. We can calculate x1. x1 is 30. Yeah. Sorry again. This is not correct. It comes to this place here. Just confusing the terms. It's good that we are marking them down. And then x1 is not 30, but it's going to be 30 minus 15 is going to be 15. There you go. Now we are correct. So we're going to have now x1, which is 15 millimeters. Let me change the color. 15 millimeters square, plus then the second area. Now the base is going to be 90 millimeters times the height is going to be 10 millimeters to the power of 3. Making some mistakes today. And divided by 12 plus the area. square millimeters times x2, which is 10 millimeters square. Let me write down here then. How much is this? Let's go back to GeoGebra and write down that other moment of inertia calculated. So it's going to be I y equals to what? So the first fraction is going to be 10 times 60 power 3 divided by 12. Yeah, plus 600 times 15 square. Then the second fraction is going to be 90 times 10 power 3 divided by 12 plus 900 times 10 power 2. Now look at that. So let me just recheck the values, 1060, 615, 90, yeah. So let me write it down before changing here. Let me see, write down, where am I? Here. So it's going to be 412500 millimeters to the power of 4 here. And let's see something visually kind of, or let's kind of to validate visually this. So the moment of inertia around the x-axis is larger than the moment of inertia around the y-axis. So kind of, this is the x-axis and this is the y-axis. So it makes sense because there seems to be more mass around the x-axis than around the y-axis. So that's why it complies with the results we're having. Yeah. So visually, you can see that the distribution of mass, or not mass in this case, because we're not talking with mass, we're not working with masses, but with areas. So the distribution of area around the x-axis seems larger than the distribution of area around the y-axis. So that's why these results might be in the right direction of what we are, let's say, trying to calculate. So perfect. Now let's do an inventory here. So we have found this value here, and the only one left to find is the product of inertia of that cross section, or the combined cross section. And the kind of that product of inertia exists because these axes xy that we are representing here are not the principal inertia axis. So that's why exists a product of inertia of in this case, or in this example, because we are not using the principal inertia axis in this case. So how to calculate the product of inertia? Well, the product of inertia is something that comes a little bit much more easier in this case. So the product of inertia here, xy, is going to be what? Well, it's going to be the multiplication of it's going to be composed or formed by two terms, and those terms are kind of similar in definition, something like that. So I'm going to just first write it down. It's going to be something like A1 times H1. How to put the actually, I believe we could use right away what we have done already here, but we need to be careful with the directions, or with the signs of this, because this takes into account signs. In this case, we can neglect some certain signs because this is just squared. So in this case, for example, if we talk about y1, for example, we said that y1 is vertical 30 millimeters, so this is positive. Y2, so y2 is measured, if we take this as a center now, is downwards, so it means that from the centroid of the section up is positive, from the centroid of the section down, then it's negative in this case. So this one is negative in this case. Then with the x happens the same. So to the right, this x1 is positive. And then this x2 that we have here, which is minus, is 10, so it's negative. So as a good note, I would say then, just to clarify, measured measured from this coordinate system. Now it makes sense like that. But now this moment of inertia, and this is okay again, because we could use it in this way, because in this equation over here, when calculated the translation, or when applying the parallel axis theorem, what's happening is that this is squared, so we can just forget about signs for a moment. But when we're talking about products of inertia, it's totally different, because this is measured with respect to the centroid, and when measured with respect to the centroid, measured with respect to G, the centroid, then we're going to have that again. X1 is going to be 15 millimeters. X2 is going to be, again, it's negative, so it's going to be minus 10. Y1 is going to be 30 millimeters. And Y2 is going to be minus 20 millimeters. Now we can complete this. So now I can write it down nicely, and this is going to be what? This is going to be, yeah, X1, Y1 plus A2, X2, Y2. That's right. So it's going to be 600 square millimeters times 15 millimeters times 30 millimeters plus, does it fit there? I believe it can fit, yeah. 900 millimeters times minus, so X2 is 10 millimeters times minus 20 millimeter, like this. So let's bring GeoGebra for this, to calculate this. All right, so it's going to be IXY equals to 600 times 15 times 30 plus 900 times minus 10 times minus 20. And that's going to give us those 450,000 value. And that's going to give here 450,000. And this is in which units? In millimeter to the power of 4. Right now we have all what we need to apply this formula here. I could write down this or copy this one here, down here. Perfect. So we can delete this and this one. Now substituting the values found here, it's going to be 2 times 450,000. Now I'm not going to use the units at this time, because the units are going to cancel out. So it's safe just to put it like this. And then this one here, 412,500 minus 151,2500. Then how much is this? So we can go to GeoGebra for this. And as we have written these values there, so we can say, well, 2 times 2 times this product of inertia, and then this is going to be this y minus ixx. And that's going to give us this 0. Minus 0.8181, let me write that down here, minus 0.818, that's a tangent of twice the angle. Then if I wanted to calculate the tangent of twice the angle, this is one trick that we need to do. So then this double angle is going to be the tangent or inverse of this value here. And that's how much it's going to be. So let's do GeoGebra. Then that's A. So how can I add tangent arc at tan, this one here. With the tangent, there is some things going on that we need to consider. This one, yeah. And let me write that down in here. So that's going to be minus 9.28 degrees. Now, this is important because with the tangent or derivating the tangent, I could try to do something here to check just tan, I believe it's this one. I'm just trying to look for the, no, it's not giving it. So the issue is with the tangent is that depending on the sign, so you would need to transpose that angle to another quadrant. For example, in this case, the tangent of this angle is in the second quadrant here. When we take about that, we take a look at the Cartesian coordinate systems, and when it is represented in the second quadrant, we need to actually transpose that angle by 150 degrees, or what it means is something like this degrees, and that's going to give us this is a nice topic actually. GeoGebra, how to say, is 180 minus, can I create alpha maybe? Oh, minus 39.28. Minus, yeah, 140 with 72. Now this is a double angle, which means that the orientation has to be that angle divided by 2. It's b divided by 2. That's going to give us 70.36 degrees. Now, if I wanted to, well, now what I need to do is represent that those 70.36 degrees now in here. So how should I do that? Well, one thing you could do is let's bring this ruler, and this will be, well, it's going to take some time because of the mouse, but I'm going to mark about 70 degrees. Is 70 degrees. I'm just going to round it up, yeah, round it completely to this value here. It's not moving. Sometimes, there you go. There it is, yeah. So put it here. And then we can draw my first inertia axis, and then the other one is going to be, well, 90 degrees apart there. Something like this. How much it would be? $70, 20, yeah, 20. Now we have found the principal axis of inertia. Something like this. Perfect. Try to see if I could. No. There it is. Let me mark down the angle here. This is 70.36. Now, this is just to cover these two first points. This one here and this one here. It's just an application of a couple of formulas, well, not a couple, a few formulas, but the true work here is to determine where is that position of the centroid of the cross-section, knowing that the combined cross-section is formed by different rectangles, and also find out how those principal inertia axes are oriented with respect to some other xy coordinate system like it is proposed here. There was a bit of changes. For example, I could mention here that I used one reference system to calculate first, for example, the centroid, and I used this blue one reference system to calculate the centroid of the whole cross section, just to position or give a position of the centroid of each of area 1 and area 2. And then I use a different reference system, for example, in the case when calculating the inertia around these two axes here that cross or passes through the centroid. So there was a bit of different coordinate system that I used there to calculate certain distances. But please keep in mind that the idea is that whatever coordinate system you use, just keep track of things so you know what measure refers to which coordinate system and so on. So at the beginning, I couldn't use any reference system kind of position on the centroid of the cross-section because I didn't know where that centroid was located. So that's why I made use of this Cartesian coordinate system, kind of inverted xy axis here. And then after having the position of the centroid, well, I use them here to calculate, for example, the product of inertia of the combined cross-section. Then after applying the formulas that we've seen in the lectures, we could find that the orientation of the principal inertia axis is at 70 degrees from the horizontal axis. And something we need to point out is that this axis here is what we have called U in the lectures, and this one here is the one that we have called VV in the lectures. Yeah, there it is. I'm going to cut the video in now because it's getting too long, but then we will jump to the other video where I present the two remaining tasks, which is finding the position and direction of the neutral axis. Well, not the position actually, because the neutral axis is going to pass through the centroid here, G. So we don't need to find the position, but the direction of the neutral axis, so how it is oriented. And then after finding that, we're going to investigate what are the maximum stresses if we use this section as a cantilever, in a cantilever arrangement with 2000 newtons applied at the free end. And yeah, we will do that in another video. See you then in the next one.